Hi, my name is Sharon, and today I'm going to be talking about how we cluster users by their energy usage, how to cluster households. And this, despite clustering being so old, this is still somewhat of an open question for energy consumption. Namely, how do we achieve the best clustering in terms of representativeness, and really how do we even identify the best clustering? So this is joint work with Ed Barber and Marta Gonzalez in the Human Mobility and Networks Lab at MIT. So why do we need lifestyle segmentation? And how can clustering help us in terms of applications? So in recent years, there's been a widespread deployment in smart meters, and this gives us the unique opportunity to identify patterns in consumption behavior and allows energy companies to assess suitability for programs such as demand response. And to achieve a good clustering, we really need to be able to capture both the time of the peaks in the load shapes. So what we have is a time series of energy usage for each household. And we also want to capture the magnitude of the total consumption for these daily load shapes. And how we accomplish this to better capture the variance, we're going to cluster on the daily load shapes themselves. So each household will be will be a mixture of the cluster centroids, depending on the makeup of their daily load shapes. Something that's also lacking in current research are actual metrics to assess the representativeness of clustering, especially just for energy consumption itself. And another thing is actually demonstrating segmentation methods in terms of applications. And we'll be going through each of these. I'll be presenting a two-stage K-means, which is a method that accomplishes both. So previous research focuses mostly on the time of the peaks. But two-stage K-means, while you could say is somewhat simple, though I prefer the term maybe elegant, but we'll be able to do both. So then we'll develop some metrics for representativeness and demonstrate an application in solar PV. So first, looking at some metrics, this first one is just the percent difference in the total consumption, the total energy used in a daily load shape. So the definition is here, pretty self-explanatory. And then we also have the peak overlap percentage. So if we have taking the red centroid over here, and the daily load shape, we want to measure how well this centroid represents the load shape. So to measure how well the peaks overlap, we take the blue area and divide that over the blue and the sum of the blue and the green areas here. So just looking at the overlap of the peaks. And these are two metrics that we can use to measure how well our clustering represents our load shapes. So moving on to a survey of some clustering methods. K-means is pretty popular in the literature. The hard assignment lends itself to interpretability. So we'll survey a baseline with standard K-means, and then also adaptive K-means introduced by Kwok and Rajagopal in 2014, where in the method we run K-means for a set minimum K, and then with the resulting clusters, if this error threshold is not satisfied, then we continue to split those clusters with K-means if K equals 2. And finally, this will give us many, many clusters. So we combine the clusters with the closest centroids using hierarchical clustering until we achieve the desired number. So another possibility is Sax Kmeans. So Sax, or symbolic aggregate approximation, is a symbolic representation of time series developed by Eamon Cog and Jessica Lin in 2007. And essentially, this is doing dimensionality reduction. So we have our time series and we break it into segments. And really, this is a z-normalized time series right here, which the authors have shown follow a normal distribution. So we determine the distance using these breakpoints where the area under this normal curve is the same. So this gives a lower bound to the Euclidean distance and essentially is a form of dimensionality reduction for K-means. So next I'll introduce two-stage K-means, which is able to cluster by both peak magnitude and consumption. So first with introducing integral K-means, this method clusters by consumption only. So in here we take the integral of the signal, essentially getting the energy consumed at each time step. So if n is 10 a.m., then we get the energy used during those 10 hours at that time step. And then we perform K-means on this integral sequence, as well as the maximum power of the load. So here you can see if you perform K-means in the integral, it gives you clusters really representing different consumption levels. And in two-stage K-means, what we do is first perform integral K-means. We achieve 3 clusters here. And then within each of these clusters, we perform standard K-means, which gives us the peak time. So over here, you can see different consumption levels as well as different peak times. So some results. First, our data is from Pecan Street. It's 15-minute granularity from the month of January and about 20,000 load profiles for 600 households in 18 cities, but mainly from Austin, Texas. So here's an example user, and you can see some of their load shapes over here. So the first step is to cluster outliers separately. We do this the same way for all methods. So if the user has over 2.5 kilowatt hours in their maximum consumption, energy consumption, then we consider them an outlier, and these can have pretty high consumption levels up to 14. So that affects the clustering a lot, which is why we do this separately. Now for the remaining, these are the resulting clusters. So we use within cluster sum of squares to determine the K. And you can see that standard K-means and Sax Kmeans really separate by time, whereas adaptive K-means for an interpretable number of load shapes, it's not necessarily the best method, because the adaptive clustering itself gives many load shapes, and then the ones with the largest size just combine together to give one cluster with 98%. So in terms of clustering by overall consumption, this is integral K-means. You can see that the differences really are just in consumption, and all of these have morning and evening peaks. In terms of these are the results for two-stage K-means, and you can see that here we have the low consumption group, the intermediate consumption bracket, and the high, ranging from 1.2 kilowatts max to 6 kilowatts max, and we can see differences in primarily morning and evening peaks, but there are also daytime peaks, which suggest some interesting heterogeneity in behavior. So unlike these previous methods, we get differences in both consumption and the time of the peaks. Just looking at the metrics that we defined previously, well, first we can measure the entropy of each household, and this is essentially the consumption pattern variability, how often the users move from load shape to load shape. So, but really I want to focus on right now the peak overlap percentage and the percent error in consumption. So with standard K-means, We have a high peak overlap percentage, which is desirable, but we also have a high error in consumption, and standard K-means really isn't able to cluster well in consumption. But we have just a comparable peak overlap for two-stage K-means, as well as much lower error in consumption. So just showing that two-stage K-means is able to cluster by both. Some of the lifestyle interpretations here, you can see that lower entropy or lower consumption users tend to have lower entropy as well, whereas higher tends to have higher entropy. And this could be explained by the fact that maybe higher consumption households tend to have more users and such, and more variability, leading to more variability. So next we'll talk about an application and how we can use this method in PV battery systems. So to use this clustering, we want to be able to use this clustering to identify users that are self-sufficient. Do they need solar? And if so, do they need a battery? So self-sufficiency is defined by the energy, the PV generated and used, divided by the total energy consumed. So it is this yellow area over here in figure A, divided by the integral of this load shape. And here, so in this figure A, we have an example of time series of 2 days, where this orange curve is the PV generated, which peaks at midday, when the sun is out. And then we see that as we as we give users more battery, then their self-sufficiency rises as well naturally, because they can store that, that energy indicated by red and use it later, such as at night. So here we will calculate the self-sufficiency values for each household. And we assign that value to the mode of its cluster. Remember, each household is a mixture of clusters. So over here, you see that standard K-means does separate self-sufficiency pretty well. There's a difference between each of the clusters. Integral K-means does not, because it only looks at consumption and not the time of the peaks, which is important for self-sufficiency. You want the time of the peaks to overlap with, to be daytime peaks to be able to take advantage of the PV generation. So two-stage K-means also has a good separation with self-sufficiency. And on the bottom, we have the storage levels. So standard K-means does not have much separation here, but integral K-means does, because it clusters by consumption, and really this is measuring how much consumption you need. That will indicate the battery capacity that you need. And you see that two-stage K-means also clusters well with respect to this. So summary, we developed some metrics to measure the representativeness of clustering, and we showed that two-stage K-means clusters with respect to both peak time and consumption, unlike previous methods. And we also showed an application demonstrating that this is a useful method for PV battery systems.